Thank you. Good morning. Thanks for coming to my presentation here today. I know that you all look closely at the conference agenda, and we had a choice this morning of presentations to attend. So actually I'm competing right now with a business presentation that's being held in one of the rooms next door on mergers and acquisitions called Preparing for Change. So actually I have a little bit of a surprise that mine is the exact same presentation. It's also Preparing for Change, except I decided to give it a slightly more technical title, and flow measurement. But it's really about preparing for change. My name is Henk, I'm the Global Director for Technical Sales and Marketing for Testing and Subsea, our well testing product service line. I'm actually standing in today for Michael Brunton, who was originally scheduled here to do this presentation. Michael is our global advisor for multiphase meters, but unfortunately he is called away on a job offshore West Africa running multiphase meters. And so I'll be doing the honors instead. Any questions that I might not be able to answer at the end of the presentation, I will definitely get Mike to follow up with us, and we'll get back to you as soon as we can. Next slide, please. Thank you. And the next one, please. So, bridging the gap between the new and the old. The existing technology, the old technology of the test separator is very well known. People are very familiar with that part. The new technology that is available now today, the multiphase meters, is somewhat unknown to some companies still. So that's really what I want to talk about now today. How can we help bridge that gap and make people more familiar with multiphase meter flow technology? No matter what role you play in the industry, it's all about the money, right? And the money is dictated by the flow of the hydrocarbons. And this implies the need for understanding how much oil, gas, and water the well is flowing. So many of you are already familiar with the well test separators. But about some 15 years ago, in Norway actually, the first multiphase flow meter technologies came on the market. And they've been generating a lot more attention in the industry since. But as you know, this industry is very slow in the uptake of new technology, so it's not as mainstream as we would like it to be. But it's definitely a very viable technology. Multiphase meters nowadays are very essential for field developments because they allow the real-time well monitoring, individual well testing, production allocation, and reservoir surveillance as well. They also provide critical information on well performance, such as water breakthrough, gas coning, and inflow characteristics. The use of multiphase meters are diverse. It ranges from onshore and offshore applications, new development projects to mature fields, wet gas, heavy oil streams. You name it, and there's an application for the multiphase meter effectively. So let's take a closer look. Since the measurement is at the core of all of our well tests, accurate metering of the well stream is a critical deliverable by which we measure the success of a well test. Conventional well test solutions using the well test separators, but the nature of this technology does not lend itself to continuous data monitoring or metering. However, when this is needed, there are some very viable alternatives out there on the market now in the form of multiphase flow meters. And the modern multiphase flow meters are capable of very accurate measurements of multiphase fluid flows, both in wet gas as well as in heavy oils, using meters as small as 1 inch all the way up to 10 inch and above, measuring across the full gas volume fraction range from 0% to a full 100% gas volume fraction. Some typical applications can include offshore and onshore exploration well test, appraisal well test, inline production testing, well cleanup optimization, production fiscal allocation, production trending, artificial lift optimization, flow rate measurements in unfavorable environments, and even in early production facilities. So a very broad range of applications for these multiphase meters. Next, please. So in order to come up with the right multiphase meter solution, we have to consider the proper design criteria. That is really important in the case of multiphase meters. Now, we can't just go out there with any multiphase meter and expect a good success. So the design considerations are really critical to the design and execution of a successful job. We use our design input forms to collect the data to help define the correct size and type of the multiphase meter. Since the distribution of the fluid phases in space and time differs for the various flow regimes, from dispersed flow, separated flow, intermittent flow, and any combination thereof, the multiphase meter is very well suited. And through our design of service process, we help find the proper meter with the right size for the right applications. And this standardized approach helps us collect the required input data processes and evaluates the data to ensure a fit-for-purpose multi-phase meter solution. And once the solution gets verified by us and by our customer, we will reference this against our own internal standards and the applicable industry standards to make sure we have a full compliant solution. Because at the end, safety of the operations is really our #1 goal. Next one, please. This is an example of our input design form that I just talked about. Now this form is really important for us as we use it now to help define and select the optimum multi-phase meter solution for the application. One of the key things that we need to enter in there is the estimated production rates for the oil, the gas, and the water. Now, this really helps us select a meter. We have a pretty broad range, but it helps us pick the right meter for the right application. And this is a key part of the design feature. There are really two broad categories of multi-phase meters out there in the industry now today, the radioactive type and the non-radioactive type. The radioactive type meters were the first meters that came to the market some 15 years ago, in the early 90s. And the the Michelson lab in Norway was the first probably to really experiment with these type of meters. Since then, there also has non-radioactive meter, and there's a couple of differences there that are worth to note. The big one is that for a radioactive meter we require PVT properties, fluid properties. So we need to sample the fluid, either do an on-site analysis or send the fluid to the lab. But we do require the input properties from the PVT analysis in order to get the correct meter readings. For the non-radioactive meter that I really like to talk about here today, we do not require any PVT properties, so it's a lot more versatile, it's a lot more flexible. The one thing that they both have in common that we always do require are the fluid densities, the phase densities of the oil, the gas, and the water. Those are rather easily obtained at the well site. Now the biggest difference again is that the PVT requirements for the radioactive meter makes it a bit more cumbersome to operate at times. It takes more intervention from the operator, so that has some downsides. Of course, having a radioactive source also brings in a couple of challenges. I can tell you some real horror stories from moving meters, radioactive meters, from one country to the other. Licensing, transportation, and logistics are becoming quite significant in that case. Also, you might not be that comfortable with leaving a radioactive source on location unsupervised. That is an advantage that the non-radioactive meters bring. We don't have any of those concerns. Those meters, however, are quite widely used, and sometimes the use is a matter of customer preference based on their prior experience. The non-radioactive meters that we use have typically four different skid sizes for portable well testing. You can see those at the top. We have skids with 1-inch meters for rather low flow rates. We have dual range meters with 2-inch and 4-inch on the same skid, 3-inch and 6-inch meter on the same skid, and then we have a 5-inch. We actually have larger sizes well available. That just depends on the application. Now this provides a very compact metering solution with an equal turn-down ratio of 100:1. This turn-down ratio is an indicator of the flow range that the meter is capable of measuring. For example, if you look at the 3 and 6-inch dual range meter skid in the third column, for example, you take a look at the liquid flow rates, ranges all the way from 500 barrels per day up to 50,000 barrels per day. Now that's your 100:1 turn-down ratio. So effectively, the meter is capable of measuring anywhere between 500 and 50,000 barrels per day. So that's one of the input designs that goes into the design phase, making sure we select the right meter. Now, if you compare it to other meters, I guess, that are in the industry, as a comparison to this 100:1 turn-down ratio, traditional Daniels or orifice plate is about 3:1. Turbine meters are about 10:1, and rotary meters are at best about 80:1. So these multi-phase meters give really a very wide range for use. Once we receive the data from the input, we evaluate it against the operating envelopes for the meters, and then we can correctly size it. That's what you see in this lower chart, where you see the two different colored lines. I have to apologize, I'm full of line, but I believe that they're blue and red. And it basically gives you like the lower boundary and the upper boundary for this particular scenario. So you see a meter range here that is capable of up to 5,000 barrels per day, and has a low limit of about 500 barrels per day. And then depending on the gas flow rate, anything that falls in between. So these would be very well suited for applications that obviously fall within this operating envelope of the meter. So it's critical that we do it up front, that we don't come to the well side with the wrong size meter, and that falls outside of the operating range. Now, the multi-phase meter, we can mount it upstream or downstream of the choke manifold. Now, it really doesn't matter because it's not dependent on the gas volume factor, on the gas volume fraction. Again, we operate it anywhere between 0 and 100% gas volume fraction. We mount it vertically with the flow traveling upwards over blind T, so we ensure proper mixing of the fluid inside the meter element. The flow, and we'll see that in a bit more detail later, but the first flow passes through an opening, an orifice, or a venturi, where we measure the first delta pressure. And then we also measure using ultrasound meters, we measure the condition of the flow itself. The nice thing about the non-radioactive meter is that there's no on-site calibration needed. The meters are effectively already calibrated in a manufacturing facility in a three-phase flow loop. The only thing that we do on the well side is kind of fine-tweaking the calibration of the meter itself. So we use the densities of the fluids, and we make sure it's properly sized. And typically that can be done in under 2 hours, so very quick. From the time that we pull up, that we install the meter, the actual on-site calibration, post-calibration really is very quick, a lot faster than what you see with the radioactive meters. It take a lot longer to install. Next one, please. So what we do with these different delta pressures, the pressure, the temperature reading, and the ultrasound, we use a mathematical modeling with a proprietary method for analysis of these non-Newtonian transient multiphase fluid flows. And this method has the capacity to identify and qualify the flow regimes. It has the capacity to measure the dynamic viscosities. And because it is viscosity and density related, we don't rely on the PVT data. And again, that is a huge plus of the non-radioactive meters. It makes it very easy now to use. So the actual measurement itself is depicted here on this slide. You see the actual meter, of course it's on the graph, it's shown horizontally, in the vertical position. It's a process pipe where the flow comes in from the left going to the right. It consists of these two flow elements, which can either be an orifice or a venturi, at locations where we measure the pressure differentials, delta pressure 1 and delta pressure 2. And there's a total of 5 sensors actually installed in the meter. These two differential pressure readings, there's an ultrasound reading, and there's a pressure and a temperature reading. So along the length between these orifice plates, an ultrasound Doppler measures the volume flow rate of the multiphase mixture, and a pressure transmitter measures the in-pipe pressure, and the temperature that you see at the top measures the inline temperature. From the signals that we get from these sensors, we can do an overall analysis of the multiphase fluid flow that provides a complete set of flow measurement data for the mixture and for each of the 3 phases consisting of the oil, the water, and the gas. So embedded computational algorithms help determine a solution for the 3 unknowns: the total liquid flow rate, the oil flow rate, and the gas flow rate. So, and these 3 variables we solve through using 3 equations. Basically, the first momentum equation that is associated with the first flow element. The second momentum equation is associated with the second flow element, and then a continuity equation across the flow element. So we have 3 equations with 3 variables, and that's how we solve for the outcomes. Comparing the non-radioactive and the radioactive meter here on this table, one of the questions that we often get asked is about resolution and accuracy. What's the difference between both types of meters? Well, regarding the meter resolution, both the radioactive and the non-radioactive meters are dependent on the lowest resolution sensors that we use, which typically are going to be the delta pressure sensors. Now that technology doesn't change from one meter to the other, so there really isn't a significant difference between the resolution of both meters. When it comes to the accuracy of the meters, we see a slight difference because the radioactive meters are dependent on the PVT properties. Any variable, any variance in the PVT properties has an impact on the calibration of the meter, and therefore on the outcome of the meter. So that's where we sometimes see a bit more variance on the accuracy between the meters. We actually have experience now with both meters. We tested both meters against each other as well, and we find the results always to be very comparable. have a slide later that shows it as well. And note also here that we talk about the installation time and the calibration time. As I mentioned on the non-radioactive meter, since the meter is already calibrated when it comes to the well side, we'll need to fine tune it, and we can do it in a couple of hours. When we talk about the PVT analysis required for the multiphase meter or for the radioactive meters, that potentially can add to the rig time allocation. So how do we deploy the meters? Well, the nice thing is that they're very compact. So we all are familiar with the test separator setups, all the associated hardware that goes around it. Of course, with the multiphase meter, very clean and simple setup that you can see here on the slide, where we have some trailer-mounted examples. Definitely allows for some very quick mobilizations and minimal rig-up time on location. What you see here is a couple of examples of multiphase meters in operation. Maybe a little bit tough to see with the lighting, but the one at the top left is an operation ongoing in Mexico, same as the one on the top right, where we actually have a little lab cabin installed in the trailer as well, where the computer is located. The bottom left picture is an operation in Iraq, and the bottom right is an operation we have going on in North Africa, in Algeria. What these examples all have in common is that these are inline production testing examples. So historically, we would have done these tests with the full test separator package. We would pull up with the test separator, we might have a choke manifold, lines, quite a few people rigging up to the well side, to the flow line, validate the flow coming from each of the different wells, do our test, move over to the next line, and go from one job to the next. Quite a lengthy procedure and involving a lot of people, involving a lot of time. The beauty now with the multiphase meter is that we can do the same thing with the multiphase meter. We just pull up with a little truck, with the flatbed or the trailer, we hook up the flow line to the multiphase meter. We get our real-time readings every second, and we switch easily over to the next well or to the next flow line. A very quick process. Obviously, what these also have in common is that there is no separation needed during these particular tests. These are inline production tests. The wells are flowing. We go into a production line, so we can really use the data to help allocate where the production is coming from. But there's no need to separate the fluid. Obviously, there's going to be instances now on the exploration or appraisal type testing where we do need to separate out the fluids. So we still require a test package out there. And actually, the job that Michael Brunton, our original presenter for today, is on a well just like that, where we have our full well test package set up, but the operator also is requesting to have a multiphase meter out there. And really, when you think about it, when we do our well tests, these big deep water exploration well tests, for example, spending lots of money, high rig rates, we're putting all our trust in that one single separator reading. Right now, we say this well is flowing X amount per day, and that's what we take as gospel for that well. But there's no way of verifying that. So what we see more and more now in our new tenders is that customers are asking for multiphase meters to be installed on those jobs as well. So we have a secondary means of validating the readings from the separator. And where we really should be, that those meters are going to be very close. If they're not very close, we know something that might be wrong, and we can make changes as needed. And we'll see that here in a later slide as well. So there's really different applications for these meters. Inline testing, allocation testing, all the way up to full exploration testing. Obviously, the nature of the multiphase meter, where that came from, where the technology was developed for in the early 90s, was for production facilities. This came from the North Sea, where they had the small production platforms, not a lot of space, yet they had to install test separator packages to help test the individual wells that are flowing on the platforms. And so they were trying to find out, is there a more economical solution that takes up less space, that is less people intensive. And that's really how the first multiphase meters were deployed for allocation testing on production platforms. And even nowadays, the companies like Aramco or Total or like Estado internationally, they will buy meters by the hundreds sometimes. We have contracts for like 200 plus meters in the Middle East, where they install them on their production facilities. The use in testing applications is relatively new and something that's gaining a lot more momentum here in the last 3, 4 to 5 years. This here is a case history in the Middle East, where we were introducing a multi-phase meter for a customer that was skeptical. They were very familiar with the test separators. They trusted our test separators, but they were willing to try this out. So we actually had a series of wells, about 76 wells that were tested. 11 tests that involved an actual third-party test separator. So it was not owned by Halliburton, it was a third-party contracted to this operator, and to keep any bias out of the equation. You can see it on this graph on the top right, where you see horizontally is the gas rate measured by the multi-phase meter, and on the vertical axis is the separator gas rate measurement. And obviously, you would like the data to be right on that straight line. And as a matter of fact, the data is very comparable to the point that we were measuring gas flow rates well over 10%. As you see in the bottom of the slide, where it is with the deltas between the different rates, very acceptable readings to the point that the customer actually is now using multi-phase meters for their inline production testing. For them, this was a really critical project. Again, lots of wells in this particular case. All the way from black oils to wet gas and everything in between. But the gas from these wells was extremely important since they needed it to provide pressure support for the rest of the field. So they really had a keen interest now to understand the different gas rates coming from the wells. And so they were not easily convinced for the use of coming up with a different technology to measure those gas rates, since they were so important to them. But at the end of the day, that's exactly what we've been using, and we're still using for the customer in that particular field, is use the multi-phase meter. This is an example where you can see that it makes sense sometimes to have your multi-phase meter hooked up at the same time as your actual separator. Here's an instance where we saw a choke change from like 72 to a 64 choke change. The separator line is the darker color, or blue, I guess, whatever it is, but the dark color, the up and down arrow, the spikes. So about a period of 4 hours, it took the separator to really stabilize and come to some sort of stable flow rate. Whereas now the multi-phase meter never really dropped a beat. We changed the choke, the rate is adjusting, and we're measuring a very stable flow rate. If you wouldn't have the multi-phase meter readings at the same time, what is happening then? You see the static spikes in the separator reading. Is it something that happened in the well? Is it something that happens in the separator, somewhere in the process? Now with the multi-phase meter, we can do a quick QA on site and see that know what is happening here. We know the flow is steady from the reservoir, so we probably have a potential issue in the separator, and we can then correct. And that really is the big reason why more and more customers now are using multi-phase meters in combination with the test separators as well. Another question that gets asked is, how do we handle solids? Multi-phase meter and solids, how does it go together? Well, the nice thing about the multi-phase meter is that effectively it's a straight piece of pipe. There's no moving parts. It's just a straight piece of pipe. And since we don't really have any intrusive parts to speak of, erosion is not a bigger issue than it would be with any other type of service piece of equipment. And we do have some significant solids though. We do require, or we do recommend to sample, so we know what the amount and the density of the material is, so we can actually use it and plug it into the calibration of the meter at the test as well. We also recommend to use a non-intrusive solids detection device, for example like a sonic device that we install at the signal of the meter, so we have a very good idea of what the volume is of the solids that are coming through. We actually are reading the total volumetric flow rate as liquid until we enter the density of the solids into the calibration process. And we can cross-check that with the solids detection device, so we can basically subtract the solids from the actual flow rates. Now that's being done by the operator on the well side, pretty straightforward operation. So we can deduct the sand or the proppant, the solids, so we actually get a solids rate as well from the total volumetric flow rate. We don't recommend to expose the multi-phase meter to more than 3% BSW for prolonged periods of time, because high solids obviously are just as erosive on this piece of metal than what they are on choke manifolds or elbows or pipes. But of course, that's all should be part of the whole screening process when we do our design considerations. Now, the presence of solids or the potential for solids is something that needs to be considered, so we can prepare for that if need to. And of course, when solids are expected, we might require some typical solids removal equipment, not unlike we would do with a normal well test operation. No difference there. So I know they're very capable of dealing with solids, but it's all down to the design, to the consideration that we place up front. You can see a typical screenshot that we have in the cabin on the computer, graphical user interface that we can configure. Basically, there's any way that might be applicable for the operation. We can show our oil rates, water rates, gas rates, pressures, temperatures, water cuts, gas volume fractions, whatever data is needed. Obviously, it's displayed there. It's recorded in real time. It's all available. The nice thing too about the multi-phase meter is that even if you find out that there is a correction taken afterwards, maybe there was new information on density, maybe there was whatever variable that changes afterwards, the raw data is always still there, so we can recalculate the same flow rates using the correct data afterwards. So it's extremely flexible. So we have to make sometimes assumptions when we set up another meter, but when more accurate data now becomes available, we can recalculate the whole data stream and correct the data. We also have an option to provide this data in real time, where we send our multi-phase flow meter data to Halliburton's Inside Anywhere platform. Now this is a generic data platform that Halliburton uses globally and gives us the ability to transmit any input data anywhere in the world. Now this could be to your office here, it can be to a central office somewhere else. It can, in some cases, even be to like a mobile device. And we can configure the data just any way that the customer sees fit. From specific line charts or bar charts, meter readings, tables, displays, whatever that we want to put in there, extremely flexible. And that's the nice thing as well, that particularly for remote operations, there's not always a need anymore to have somebody out there at the well site, and we can transmit that data to a remote location, or from a remote location back to a central location. Okay, so how are we going to bridge this gap? How are we going to move from the existing well test technology, the test separators, to the multi-phase meter technology? The non-radioactive multi-phase flow meter technology is readily available, and we have proven its merit. There's some really good measurement performance which has been demonstrated and proven in several blind taste tests, as well as in real field operations, especially in the whole range of gas volume fractions from 0 to 100%. And I think that's really critical. We don't need to have a separate meter for like a water cup meter or a black oil meter. We can use the same meter range. This technology also bridges the gap in our ability to deliver more advanced functions and provides the accurate measurements on a consistent basis that help improve the QA/QC compared with the conventional technology on the market. The technology is very robust to variations in the configuration parameters, like I just talked about, unlike some other conventional metering technology. We can measure extremely fast measurements, as much as a reading per second, that captures the rapid fluctuation in the flow. For example, slug flow. The multi-phase meter will quickly identify slug flow as well, for example. And then you add to that the ability to provide the quick in situ verification and self-diagnostics. And it provides a pretty easy and in our opinion, a winning concept for multi-phase flow meters. So last but not least, thanks for listening here to my Dutch accent. I'd like to thank the Midland Energy Expo as well to give us an opportunity here today to talk about multi-phase meter technology that we believe is very exciting, has a lot of applications, complements the existing technology that is out here. It's not a one-stop solution, but it's another tool in our portfolio that we can deliver when it comes to metering and measuring fluids. So since we still have some time, I'd definitely be willing now to answer any questions. As I said, if I don't have the answer, we will get the answer for you and get back to you and then, in due time. So, thanks. Yes, sir.
What about, you talk about calibration and then going back, if you make some assumptions and you have to go back and maybe redo some of the production, how is that with customers, or how exactly do they, how does that go along? Does that cause problems sometimes, or is that an issue?
Well, as long as you're transparent in that, I think that is what we found is the key thing. And as a matter of fact, we have actually done these blind taste tests, right? We've tested our meter against the test separator. We've also tested our meter against competitor meters. And what we found is that as long as everybody understands what the process is, so the key thing is that the meter will always record the raw data sets, and then we can manipulate it through calibration and come up with the readings. But if we have data that is changed afterwards, or somebody gave us like the wrong input and corrects it later, we'll show that whole that whole history. So it's a transparency, I think, in the reporting that makes it acceptable to customers. Now, we haven't experienced any issues. We've seen some other examples of other companies where that wasn't the case, because since you can manipulate the data, sometimes that gets used for with the wrong intent as well. Not unlike, for example, in a different area like memory gauge data. We know what happens there sometimes as well. But as long as there's transparency, we provide the raw data, we provide the calculated data, and if there is a need to make a change, we're very transparent in that process. So we haven't seen any. The nice thing is that you are able to do it, which is a lot more difficult, of course, in conventional test separated type of setup.
What about in places where when you go into a new field, there almost has to be some sort of something to compare it to? Right. There's always generally a separator or something somewhere you can isolate to know going in. Yeah. I mean, the nice thing is that since we have this very large turn down factor, right? So there's 100 to 1. So it's not very likely that we come up with the wrong meter for that particular field application. I mean, we'll have a pretty good idea where the flow rates normally are, even in exploration wells. I mean, there's normally a pretty good understanding of where it is. That's also the reason why we now start to deploy some of these dual range meters, so we can really increase the operating envelope of the meters as well. But it can switch.
You can switch, exactly. But it's really, the key for us is that the upfront design is critical, and it's often overlooked by sometimes by customers who just want to rush, and a meter is a meter, and to send it out there and we'll make it work. No, I mean, it's a little bit of effort up front to really understand what the application is and what the right size meter is that can make the difference between a successful job and not a successful job. It's not like any other job, right? I mean, it's the planning that really dictates the success of the overall job. Especially in the case of multi-phase meters, we really need to understand up front what we're getting into and what the new applications are. But once you're in this particular field, you have a pretty good idea of typical flow rates, where you will end up. And again, the ability to have to dual range meters really makes an envelope even bigger, and lets us really make some good changes. Yes, sir.
What's the acceptable range of error when it comes to repeatability in the data measure? Because you showed a slide that had the gas flow rates, you're looking at 89%.
Right.
And for liquid flow rates, you're looking at 5%.
Yeah.
So what's industry standard as to what's acceptable?
There's and I don't think there's an it's one before this. Yeah, there's one here. Yeah. I don't think that there is a scientific basis for it, but we've always, the rule of thumb, I guess, that's commonly used is that if you're within 10%, you're in a good range, right? And that's really what we've seen. For example, this particular project, and there's some more in the same area that we have done. When we challenged the customer to give us an opportunity to run the load-based meter, that was the challenge that we gave. So it has to be within 10% of our test separator numbers. And that's exactly where we ended up. In this particular case for this customer, anything that went over 10% was not acceptable.
The trick is knowing what you're measuring against also.
Exactly, yeah. And that's the beauty of the multi-phase meter, though, is that you can really in the flow loop design, or in the flow loops where we calibrate the meters, I mean, that's a known, that is a 100% known fluid, right? So that's really where the calibration takes place. So we can be absolutely certain that when we test on a meter in the flow loop, we know exactly what the flow rate should be, and we calibrate the meters for it. So we really are fine-tuning that on location for the specific fluid properties that are out there. Right.
On those trailers that you had, is there a flow loop on there where you can go back and, you can test on those trailers, portable trailers that you have?
No, there's not I mean, no, we would go straight from,
There's no flow loop?
no, there's no flow loop there, no. I mean, there's a bypass obviously, but there's no flow loop.
You use the same meter there, whether it's wet gas or
Same, yeah. And the beauty of this particular meter is that it measures across the whole range, 0 to 100% as volume fraction. So even if it's like a wet gas, we don't have to change that meter, which is pretty unique. Is anybody using multi-phase meters here in Midland that you're aware of? You haven't come across them.
More people they won't look at some because one of the issues they're having down there is the one is well allocation and the other is the paraffin is so bad that it plugs up the turbine meters even after they separate it, so they're having trouble with the turbine meters. And they're looking for alternatives.
Right. Be a great way to try it.
Yeah.
Yeah.
But there's quite a difference from the turbine meter.
Well, you have the trailer with it too. I've never seen a turbo meter on the trailer.
Wheels, take a wheel off, I guess, and just leave it there.
Yeah.
I think it's actually fairly comparable if you look at the actual overall production plant
Yeah.
that has to feed into that turbine meter. You're replacing all of that upstream equipment. You don't have any moving parts, it's personnel to run it. So it's actually, from the economics perspective, I think it's really where this meter is unique and an opportunity to make a difference.
You get the visualization of the data in real time.
Yeah.
24 hours later, if you had to make a change or correction back on talking about it, you do that.
Yeah, and I think the other thing that makes it unique as well, I mean, you can leave it basically by itself, right? I mean, it's a piece of pipe. It's recording data, but there's no moving parts, so you can have it there for quite an extended period of time, measuring your data the whole time. I mean, it gives you a little more flexibility. Okay.
Is Halliburton using several kinds, or you just got more to the one that uses the differential pressure?
Yeah.
Are you
Interestingly,
trying to focus on one now, or?
Yeah, we don't have our own Halliburton multi-phase flow meter. We've taken a different path than some of the competitors out there. Since there are so many multi-phase flow meters now in the industry, and we often found that customers may have specific demands for customer or for a certain type of meter as well, based on prior experience and what they were familiar with. So that's the approach that we have taken, that we will provide the meter that the customer is asking for. Here in the last couple of years, we really are not trying to standardize much more on this particular non-radioactive multi-phase meter, since we've had such good experience. We've tested it against the radioactive meters, we've tested it against the test separators. We have a lot of customer validation for this particular meter. So we're very comfortable with it. And that really is the meter that we would choose if you have to feed them, not to choose or select another multi-phase meter. It's compact, much more economical than what you would think. Because if you're familiar with multi-phase meters, there definitely are some Rolls Royces out there that may be fine for the Rolls Royce application, but that's really not what we're targeting here. I think what we can offer now today is to find a lot more economical than what people might be used to in the past. I think if pleasantly surprised there. So yeah, it's now that's really is the kind. I mean, of course, there is from like a service company perspective, not having radioactive materials is a great plus. Because that's an absolute nightmare. Once they're in country, it's one thing, but even moving it from one location to the other, maybe across county lines or state lines, and it's just hassle that you don't really need if you don't have to. And now with the technology that's out there, we don't have to meters now. And these meters, in our experience, and we've tested them against meters that we provided, we've tested them against radioactive meters that other companies provided. They're as good, if not better, than what is out there today. So these are well-matured meters, well-proven, and more and more customers are using them every single day. So that's really what we're trying to do. Thanks very much.
So join me in thanking Henk.